For question 1, before proceed to preparation of natural rubber band, let's know the definition of natural rubber. Natural rubber is the addition of polymer that obtained from tropical rubber tree as milky white fluid called latex. The top countries to produce rubber are Brazil, India, Indonesia, Sri Lanka, and our country Malaysia. It is made by polymerization of isoprene with chemical formula 5 carbon, 8 hydrogen, and known as 1,4-polyisoprene. So first step of tire manufacture is to extract natural rubber. It is obtained by tapping the heavier Braziliensis tree until a milky fluid called latex appears. The latex contains rubber particles suspended in water. The next step is to coagulate the rubber particles by adding an acid like acetic acid or by using other coagulants. The acid causes the rubber particles to clump together and separate from the watery part of the latex. After that, the coagulated rubber is washed to remove impurities and excess acid. The resulting material will form soft crumb-like pieces. Then dried to remove excess moisture. The dried rubber is then masticated, which is a mechanical process that involves kneading and rolling the rubber. This process helps to break down larger rubber molecules into smaller ones. Next, the key process is vulcanization that gives natural rubber by treating it with sulfur and heat. The sulfur atoms form cross-link or bridge between the long chains of rubber molecules. These cross-links give rubber its elasticity, strength, and durability. The last step is to vulcanize and shape into the tire. The exact mechanism of cross-linking is complex and involves multiple steps. Firstly, sulfur molecules are mixed with the rubber to form cross-link between long chains of rubber molecules under heat and pressure, typically around 140 until 160 degrees Celsius or 284 until 320 degrees Fahrenheit. The sulfur atoms start reacting with certain functional groups on the rubber molecules. This forms bridge between adjacent polymer chains, creating a three-dimensional network. This network structure gives vulcanized rubber to improve properties such as elasticity and resistance to heat and chemicals. The main chemical in natural rubber is isoprene. To detect this chemical, instruments such as gas chromatography is suitable due to involve the thermal decomposition of the sample to produce volatile compounds that are then separated and analyzed. Besides, gel permeation chromatography is able to separate and quantify the components of a mixture. Furthermore, infrared spectroscopy such as FTIR can use infrared radiation to obtain an infrared spectrum of absorption of solid, liquid, or gas. All of them are great for identifying and quantifying chemical compounds in natural rubber. The primary compound in natural rubber is polyisoprene, which is polymer derived from the monomer isoprene. There are 4 isomeric forms of polyisoprene as shown in the figure, which are trans 1,4 addition, cis 1,4 addition, 1,2 addition leaving a pendant divider group, and 3,4 addition. There are 2 types of polyisoprene, which are natural and synthetic. The difference between both is depend on composition. Natural polyisoprene derived from latex of the heavier Brazilian tree, while synthetic polyisoprene is produced through a synthetic process. The synthetic process results in a purer product. Next, natural polyisoprene has a slightly better properties in terms of tensile strength, tear resistant, compression set, and flex fatigue resistant. Synthetic polyisoprene offers more consistent dynamic properties and better weather resistant due to its purity. Lastly, synthetic polyisoprene is odorless, while natural polyisoprene may have a slight odor due to presence of organic compounds. Next is the properties of polyisoprene. First is high resilience, which can withstand high pressures without significant deformation. This property is crucial to maintain its shape under pressure. Second, excellent elasticity, which allows it to return to its original shape after being deformed. This characteristic is essential for products that need to absorb and dissipate the energy. Third, resistant to tear and abrasion, making it suitable for application where the material is subjected to wear and tear. Flex fatigue resistant, meaning can withstand repeated flexing without significant loss of strength or elasticity. Besides, good chemical resistance includes oil, fuels, and acid for use in environments where this substance will contact. Lastly, low temperature performance down to negative 65 degree Fahrenheit, making it suitable for use in cold climates. Application of polyisoprene. The first one is tire manufacturing. Natural rubber with its excellent elasticity and abrasion resistant provide grip, durability and shock absorption for tires used in vehicles. Next is industrial applications such as automotive and packaging, production of hoses, belts, and other flexible components. Pads on rubber will provide grip and durability. Furthermore, medical devices such as gloves, tubing, catheters, and seals due to its biocompatibility and flexibility. Besides the elastic and water-resistant properties of natural rubber make it common material for shoe soles and rain boots. Polyester also used in shock absorbers to absorb and dissipate energy, providing a smoother ride for passengers and reducing wear on vehicle suspension system. Lastly, in the production of seals and gaskets due to withstand high pressures and resist wear and tear, make it suitable for this application. For the next question, before proceed to the method production of acetone, let's look about what is acetone. Acetone is a volatile liquid that belongs to ketone family with the chemical formula 3 carbon, 6 hydrogen, and oxygen. It has a molecular weight of 58.08 gram per mole and is known for its sweet and pungent odor. Acetone is miscible in water and most organic solvents with a boiling point of 56.05 degrees Celsius and melting point of negative 94.7 degrees Celsius. Its high polarity, low viscosity, and low surface tension contribute to its excellent solvent properties. The first method for production of acetone is cumin process, which known as Hock process. The process was invented by R. Udrich and P. Sergevey in 1942 in the USSR and independently by Heinrich Hock in 1944. This method for synthesizing phenyl and acetone from benzene and propylene. This process is significant for its ability to convert two relatively cheap starting materials, benzene and propylene, into two valuable products, phenyl and acetone. It is the primary method for producing phenyl and acetone on a large scale, with nearly 10.8 million tons of phenyl produced by this process in 2022. The second method is reaction from alkenitriles. These involve a two-step process that begins with the reaction of grenade reagent with an alkenitril followed by hydrolysis. Acetonitrile reacts with a grenade reagent such as methyl magnesium bromide to form a grenade product. This reaction is a nucleophilic substitution where the nitrile group is replaced by the grenade reagent, produce highly reactive intermediate. The grenade product is then hydrolyzed in an acidic medium and breaks down the grenade product, leading to formation of acetone and magnesium salt. The third method is hydrolysis of gem dihalide, which contains two halogens such as chlorine, as the figure above 2,2-dichloro-propane undergoes alkaline hydrolysis, which is a reaction with water in the presence of an alkene solution such as sodium hydroxide. This reaction breaks down the gem dihalide into simpler compounds, including ketones. During the hydrolysis of gem dihalides, one of the halogen atoms is replaced by a hydroxyl group, and the other halogen atom is replaced by a hydrogen atom. This process results in the formation of acetone and other products. Next method is oxidation of isopropyl alcohol, which involves a process known as dehydrogenation. This method is particularly relevant for industrial production due to produce high concentration of high purity acetone. This process starts when isopropyl alcohol is subjected to catalytic dehydrogenation, a chemical reaction that removes hydrogen from the molecule. This reaction is typically carried out in the presence of catalyst, which accelerate the reaction without being consumed. The hydrogenation of isopropanol result in the formation of acetone, a ketone. The last method is ozonolysis of alkenes. This process involves two steps of reaction which start with alkenes such as 2-methyl-2-butene treat with ozone in a reaction known as ozonolysis. This reaction breaks the carbon-carbon double bond in the alkene, generating an ozonide intermediate. The ozonide is a highly reactive species that can be unstable and potentially explosive. The ozonide intermediate is then treated with a reducing agent such as zinc to convert it to carbonyl compounds. Depending on the structure of starting alkene, this step can produce aldehydes or ketones. For 2-methyl-2-butene, the reduction results in the formation of acetone and acetaldehyde. Let's proceed to the chemical mechanism of the production of acetone through the cumene process. There are three steps of mechanism starting with the protonation and water loss. Initially, cumene react with oxygen to form cumene hydroperoxide. The OH oxygen of the peroxide is protonated, creating a good leaving group. This is following by rearrangement where the phenyl group shift from carbon to an oxygen with a simultaneous loss of water. Next is addition of water and photon transfer. The resulting carbocation intermediate is attacked by the nucleophilic water to form a protonated hemiacetal. A hemiacetal is a compound with an ether group and a hydroxide group bonded to the same carbon atom. A photon transfer occurs with the oxygen near the ring taking the extra hydrogen. Lastly, elimination reaction occurs which form the C double bond O bond in the product of acetone and eliminating phenyl ester at the product.
Ethylene hydration is a chemical process where ethylene reacts with water in the presence of catalyst to produce ethanol or ethylene glycol, depending on reaction conditions such as temperature, pressure, and catalyst concentration. Ethylene hydration can yield different products. Ethylene hydration has significant industrial application. Ethanol produced via ethylene hydration is used as a biofuel additive, solvent in the chemical industry, and raw material for the synthesis of various chemicals. Ethylene glycol is utilized in the production of polyester fibers, resins, antifreeze solution, and other industrial applications. The Shell Oil Company first employed this catalyst for large-scale ethanol production in 1947. This indicates that the process has been utilized for several decades and has historical significance in the chemical industry. Ethylene is widely produced chemical with various industrial applications, so it's generally available from several sources. Here are some common ways to obtain ethylene. 1. Petrochemical plants. Ethylene is primarily produced on a large scale in petrochemical plants through the steam cracking of hydrocarbons, such as ethane, propane, or naphtha. In this process, high temperature steam is used to break down the hydrocarbons feedstock into smaller molecules, including ethylene. Petrochemicals plants are major producer of ethylene and supply it to various industries worldwide. 2. Many chemical suppliers and distributors offer ethylene gas in the compressed gas cylinders or as a liquefied gas. These supplies serve a wide range of industry, including pharmaceuticals, plastic, agriculture, and manufacturing. 3. Industrial gas companies produce and supply ethylene as part of their portfolio of industrial gases. These typically offer ethylene in bulk quantities and can provide storage and delivery solutions tailored to the needs of the industrial customer. The reaction is carried out with an excess of high pressure steam at 300 degrees Celsius or 572 degrees Fahrenheit. High pressure and temperature are necessary to drive the reaction forward and achieve reasonable reaction rate. The mechanism that occur during this process are protonation of ethylene. In the presence of an acid catalyst, ethylene is protonated. This protonation occurs at one of the carbon atoms in the double bond, forming a carbocation intermediates. The protonation step is the slow rate determining step of the reaction due to the high energy required to break the pi bond in ethylene. Nucleophilic attack by water. A water molecule acts as a nucleophile, attacking the positively charged carbon atom in the ethyl carbocation. The nucleophile attack leads to the formation of a protonated ethanol intermediates. This step is relatively fast compared to the protonation step. Deprotonation process. The protonated ethanol intermediates undergo deprotonation, resulting in the removal of a proton. This deprotonation step can occur through several pathways. One possibility is the abstraction of a proton by another water molecule present in the reaction mixture or by the acid catalyst itself. This leads to the formation of ethanol. Regeneration of the acid catalyst. After the deprotonation step, the acid catalyst is regenerated and can participate in subsequent cycle of the reaction. In the case of sulfuric acid, it can be regenerated by reacting with water to form hydronium ion and sulfate ion. The recovery and purification steps in the production of ethanol from the direct hydration of ethylene involve separating ethanol from the reaction mixture and purifying it to obtain product of the desired concentration and purity. Separation of ethanol water mixture. After the reaction, the mixture typically contains a mixture of ethanol, water, unreacted ethylene, and possibly other byproduct or impurities. The first step in the recovery process is to separate the ethanol water mixture from the unreacted ethylene and other components. This separation is often achieved by using a phase separation method such as decantation or centrifugation to separate the aqueous and organic phases. Fractional distillation. Once the ethanol water mixture is separated, it undergoes fractional distillation to separate ethanol from water. Fractional distillation takes advantage of the difference in boiling point between ethanol, which is 78.2 37 degrees Celsius and water 100 degrees Celsius at standard atmospheric pressure. In the fractional distillation column, the mixture is heated and the vapors rise through a series of trays or packing materials. As the vapors cool and condense at different height in the column, the ethanol-rich vapor is collected at a certain level, while the water-rich liquid is collected at a lower level. This process allows for the separation of ethanol and water into different fractions. Rectification, also known as refluxing or rectifying distillation, is a process used to further purify the ethanol fraction obtained from the fractional distillation. In rectification, the ethanol vapor is passed through a fractionating column with additional trays or packing material. The rising vapor comes into contact with descending liquid reflux, which helps to enhance the separation efficiency by promoting equilibrium between the vapor and liquid phase. This process allows for the removal of remaining impurities and water from the ethanol stream, resulting in a more concentration and purified ethanol product. The production of anhydrous ethanol involves further dehydration of the purified ethanol obtained from the recovery and purification steps. Anhydrous ethanol refers to ethanol with minimal water content, typically containing less than 1% water by volume. Dehydration. After the purification process, the ethanol product may still contain traces of water. To remove the remaining water and obtain anhydrous ethanol, the purified ethanol stream undergoes dehydration. There are several methods of dehydration, but one common approach is molecular sieve dehydration. Molecular sieve dehydration is widely used method for removing water from ethanol. In this process, the purified ethanol stream is passed through a bed of porous solid material known as a molecular sieve. The molecular sieve has a highly porous structure with precise pore size that selectively absorb water molecule while allowing ethanol molecule to pass through. Adsorption of water. As the ethanol stream flows through the molecular sieve bed, water molecules are adsorbed onto the surface of the molecular sieve particles due to the affinity for polar surface. Ethanol molecules which are less polar pass through the molecular sieve unaffected. This selective adsorption process allows for the removal of water from the ethanol stream. Regeneration of molecular sieve. Over time, the molecular sieve becomes saturated with adsorbed water molecules and lost its dehydration capacity. To regenerate the molecular sieve and restore its adsorption capacity, it is heated to a high temperature, typically in the range of 150 degrees Celsius to 250 degrees Celsius. This heat treatment drives off the adsorbed water molecules, leaving the molecular sieve ready for use in the dehydration process. Once the ethanol has been dehydrated to the desired level, it is typically collected and stored in the suitable containers or tanks. Anhydrous ethanol is highly susceptible to water absorption from the atmosphere. So it is important to store it in sealed containers to prevent contamination and maintain its purity. These are the simple process diagram of the direct hydration of ethylene. Ethanol, also known as ethyl alcohol, is a versatile chemical compound with a wide range of applications across various industries. Some of the common use of ethanol include use as a biofuel additive in gasoline to reduce emission and improve octane ratings. Ethanol blended fuels such as E10 and E85 are used in vehicles, especially in countries with renewable fuel mandates. Solvent. Ethanol is a highly effective solvent and is used in the manufacturing of paints, varnish, coatings, and cleaning products. It is also used as a solvent in pharmaceuticals, cosmetic, and personal care products. Alcohol beverage. Ethanol is the primary alcohol found in the alcoholic beverage, such as beer, wine, and spirits. It is produced through fermentation of sugars by yeast and contributes to the flavor, aroma, and intoxicating effects of the alcoholic drinks. Chemical intermediates. Ethanol serves as a key intermediate in the synthesis of various chemicals and pharmaceuticals. It is used in the production of acetic acid, ethyl acetate, ethylene, and other organic compounds. The raw material of ethanol production can be from ethylene, sugars, starchy materials, and lignocellulosic materials. Ethanol production of starchy materials. Starchy materials such as corn, wheat, potatoes, and cassava are commonly used as feedstock for ethanol production. These materials contain complex carbohydrates in the form of starch, which consists of long chain of glucose molecules. Starchy materials are first cleaned and ground to increase surface area and facilitate the hydrolysis process. The ground material is then mixed with water to form a slurry or mash, which is suitable for enzymatic hydrolysis. Enzymatic hydrolysis, also known as saccharification, is the process of breaking down complex starch molecule into fermentable sugars, which is glucose. Enzymes such as alpha amylase and glucoamylase are added to the mesh to catalyze the hydrolysis of starch into shorter chain of glucose molecules. Alpha amylase break down the starch into dextrin, which is shorter chain of glucose, while glucoamylase further breaks down the dextrin into glucose. Once the starch is hydrolyzed into fermentable sugars, fermentation can proceed. The mash containing the fermentable sugar is inoculate with yeast, typically strain of Saccharomyces, to initiate fermentation. Yeast cell metabolize the glucose through glycolysis, converting it into pyruvate and generating ATP and NADH in the process. Pyruvate is then decarboxylated to acetaldehyde, which is subsequently reduced to ethanol by alcohol dehydrogenase, producing NAD plus as a cofactor. After fermentation, the resulting mixture known as beer or mash containing ethanol, water, unfermented sugars, yeast, and other byproduct. The beer is then distilled to separate ethanol from the mixture. Distillation involves heating the beer to vaporize ethanol, then cooling and condensing the vapor to obtain liquid ethanol with higher concentration. Multiple distillation steps may be required to achieve the desired purity of ethanol, typically around 95 to 99% pure, and hydrous ethanol containing less than 1% water by volume can be obtained through further dehydration process if required for certain application. Ethanol production of sugar. Ethanol can be produced by various sugar-rich feedstocks, including sugarcane, corn, wheat, and molasses. The choices of feedstock depends on the factors such as availability, cost, climate suitability, and regional preference. The first step in ethanol production from sugar is to extract fermentable sugar from the feedstock. For sugarcane, the cane is crushed into extract juice rich in sucrose. For corn, wheat, or other grains, the starches are hydrolyzed into fermentable sugars using enzyme. Molasses, a byproduct of sugar refining, contains sucrose and other sugar and can also be used as a feedstock. Fermentation is a biochemical process where microorganisms convert sugar into ethanol and carbon dioxide in the absence of oxygen. The extracted sugars are mixed with water and yeast in large fermentation tanks or vessels. The yeast metabolize the sugars, breaking them down into ethanol and carbon dioxide through anaerobic respiration. The fermentation process is typically carried out under controlled conditions of temperature, pH, and nutrient availability to optimize ethanol production. Then distillation and ethanol recovery, same as starchy materials. Alongside ethanol fermentation process also produce carbon dioxide, yeast biomass, and residual solids. Carbon dioxide is often captured and used in various industries, including food, beverage, agriculture, and pharmaceutical. Yeast biomass and residue solids may be further processed into animal feed or other value-added products. The fermentation process involves several biochemical steps and mechanisms within yeast cells to convert sugars into ethanol and carbon dioxide. The first step in fermentation is glycolysis, a metabolic pathway that occurs in the cytoplasm of yeast cells. During glycolysis, glucose, a 6-carbon sugars, is broken down into 2 molecules of pyruvate, a 3-carbon compound. This process involves a series of enzyme catalyzed reactions, including phosphorylation, isomerization, and oxidation reduction reaction. ATP is produced as a source of energy for the cells, and NADH is generated as a reducing agent. Pyruvate decarboxylation. The pyruvate molecules produced during glycolysis are transported into the mitochondria of yeast cells. Within the mitochondria, pyruvate undergoes decarboxylation, a process where a carboxyl group COOH is removed from pyruvate, forming a acetaldehyde, a 2-carbon compound, and releasing carbon dioxide. The reaction is catalyzed by the enzyme pyruvate decarboxylase. Ethanol formation. Acetaldehyde, the product of pyruvate decarboxylation, is then reduced to ethanol by the enzyme alcohol dehydrogenase. NADH generated during glycolysis serves as a cofactor for the reduction reaction, converting acetaldehyde into ethanol while regenerating NAD+. One of the critical aspects of ethanol fermentation is the regeneration of NAD+, which is required to sustain glycolysis. The reduction of acetaldehyde to ethanol by alcohol dehydrogenase serves this purpose, as it consumes NADH and produces NAD+. Without NAD+, glycolysis will cease, and the production of ATP, which is essential for cellular metabolism, will be halted. Introduction to urea. Urea is an organic compound with the chemical formula CONH22, is one of the simplest organic compounds and is composed of carbon, nitrogen, oxygen, and hydrogen atoms. Urea is commonly found in the urine of mammals as a waste product of protein metabolism. It is also synthesized industrial for various applications across different industries. Applications. Granular urea is widely used nitrogen fertilizer in agriculture. Is produced in the form of uniform-sized granules, typically ranging from 2 to 4 millimeters in diameter. These granules are coated with protective layer to prevent moisture absorption and minimize nitrogen loss through volatilization. Granular urea provides plants with a readily available source of nitrogen essential for their growth and development. This spread across field using butylene, also known as butane, is a group of hydrocarbons classified as olefins. It belongs to the alkene family and is composed of 4 carbon atoms with varying degree of unsaturation. Butylene exists in several structural isomers, including 1-butane, cis-2-butane, trans-2-butane, and isobutylene. Each isomer differs in the arrangement of atom and the location of carbon-carbon double bonds, leading to distinct chemical properties and application. Butylene are colorless gases at room temperature and pressures, with boiling point ranging from approximately -6 degrees Celsius to -34 degrees Celsius. They are flammable and readily undergo combustion in the presence of oxygen, producing carbon dioxide and water as combustion products. Butylene are important industrial chemical used for feedstock in various processes, including petrochemical production, plastic manufacturing, fuel refining, and chemical synthesis. They serve as valuable intermediates in the production of polymer, solvents, fuels, and other organic compounds. Due to their versatile nature and reactivity, butylenes find applications across a wide range of industries, from automotive and construction to packaging and agriculture. Their ability to undergo polymerization, alkylation, and other chemical reactions make them indispensable in modern industry process. Butylene play a crucial role in the petrochemical industry, particularly in the production of butadiene, a key monomer used in the manufacture of synthetic rubbers and plastics. Butadiene is produced through the catalytic dehydrogenation of butylenes, primarily 1-butane, cis-2-butane, and trans-2-butane. It serves as a vital building block for the production of synthetic rubber, which finds widespread application in tire manufacturing, automotive components, hoses, and belts. Butadiene unique properties, including elasticity, durability, and resistance to abrasion, make it indispensable in various industry applications, driving for the demand for butylenes as feedstock in the petrochemical process. In the plastic industry, butylenes are produced in the production of polybutylene (PB), a thermoplastic polymer known for its excellent chemical resistance and flexibility. Polybutylene is synthesized by polymerizing 1-butane or a mixture of butylenes, yielding a material with unique properties suitable for various applications. Polybutylene is commonly used in plumbing systems for hot and cold water distribution due to its low cost, ease of installation, and resistance to corrosion and scaling. Its versatility and durability make it preferred material for plumbing pipes, fitting, and connectors, contributing to its widespread adoption in the construction and building industries. Butylenes serve as important components in the fuel industry, particularly in the production of gasoline and alkylate. Isobutylene, a type of butylene, is a key raw material used in catalytic alkylation reaction with isobutene to produce alkylate, a high-octane gasoline blending component. Alkylate is prized for its excellent anti-knock properties, which help to improve the octane rating of gasoline and reduce engine knocking and pinging. As a result, butylene, especially isobutylene, play a significant role in enhancing performance and equality of gasoline fuels, contributing to the efficiency and environmental sustainability of automotive transportation. Butylene serve as important intermediates in chemical synthesis, contributing to the production of various organic compounds used in diverse applications. Isobutylene, in particular, is a key raw material in the production of butyl rubber, a synthetic elastomer with exceptional impermeability to gases and liquids. Butyl rubber is synthesized by polymerizing isobutylene with a small amount of isoprene, yielding a material with unique properties suitable for tire inner tubes, adhesive, sealants, and other industrial applications. Additionally, butylenes are utilized in the synthesis of synthetic lubricants, surfactants, and other specialty chemicals, highlighting their versatility and importance in chemical manufacturing process. The milling process of palm oil. Mature palm fruits are harvested from oil palm tree. This process involves carefully cutting the fruit bunches from the trees using specialized harvesting tools. The timing of harvesting is critical to ensure optimal fruit ripeness and oil yield. The sterilization process aims to deactivate enzymes and reduce microbial contamination in the harvested palm fruits. Large vessels such as sterilizer or autoclave are commonly used for sterilization. These vessels are equipped with steam coil or jacket for heating. This way, harvested palm fruits are transported to the processing facility for sterilization. The fruits are loaded into the sterilization vessels, which is then sealed to create a controlled environment. High-pressure steam is injected into the vessel, heating the fruits to temperature typically ranging from 120 to 150 degrees Celsius. The fruits are held at the sterilization temperature for a specific duration, typically ranging from 55 to 90 minutes. This duration ensures through the activation of enzyme and microbial reduction. After sterilization, the fruits are cooled using water or air to stop the heating process and prevent overcooking. The stripping process involves separating the sterilized palm fruits from the fruit bunches. Rotating drum strippers or mechanical threshers are commonly used for stripping. This way, the sterilized palm fruits along with the bunches are loaded into the stripping equipment. The rotating drum stripper or thresher mechanically separate the fruits from the bunches. The rotating motion and mechanical action help dislodge the fruits from the bunches. The separated fruits are collected and transferred to the next processing stage, while the empty bunches are discarded or used for other purposes such as biomass or compost. The digestion process aims to break down the cell structure of the fruit pulp to facilitate the extraction of oil. The digestion process typically takes place in a steam heated digester, which is large vessel equipped with steam coil or jacket for heating the fruit pulp. After sterilization, the sterilized fruits are mechanically crushed and or shredded to create a homogeneous fruit mesh. The fruit mesh is then transferred to the digester, where it is heated under high temperature and pressure using steam. The high temperature and pressure in the digester help breaks down the cell wall of the fruit pulp, releasing the oil trapped within the cell. The duration of digestion varies depending on factors such as fruit ripeness and processing condition. Typically, the pulp is heated for the specific period to ensure true digestion. The pressing process involving extraction the oil from the digested fruit pulp. Various types of mechanical press are used for oil extraction, including screw presses, hydraulic presses, and expeller presses. This is where, after the digestion, the heated fruit pulp is then transferred to the pressing machine. In the pressing machine, the fruit pulp is subjected to the mechanical pressure to squeeze out the oil. The pressing process may involve a single pressing or multiple stages of pressing to maximize oil extraction efficiency. The extracted oil, along with some solid residue, is discharged from the pressing machine. The oil solids mixture is then separated using methods such as centrifugation or filtration to obtain crude oil. After pressing process in palm oil production, the extracted material typically separate into two main components, diluted oil and press cake. Diluted oil refers to the crude palm oil, CPO, obtained from the pressing process. It is the primary product of oil extraction and contains a mixture of triglyceride, fatty acid, along with impurities such as water, solid, and other non-oil components. Press cake, also known as palm kernel cake, PKC, is the solid residue remaining after oil extraction from the fruit pulp. It's primarily consists of fibrous material, residue oil, and other non-oil components such as protein and carbohydrate. The process for the diluted oil. The purification process aims to remove impurities such as fatty acid, phospholipids, and other non-triglyceride components from the diluted oil. Purification typically involves mixing the diluted oil with an alkaline solution in a reaction vessels. This is where the diluted oil mixed with alkaline solution to neutralize the fatty acid present in the oil. This reaction forms soap, which can be easily separated from the oil. After neutralization, the mixture is allowed to settle or undergo centrifugation to separate the soap and other impurities from the oil. The purified oil, known as neutralized oil, is then separated from the impurities. The clarification process further removes solid impurities, water, and other non-oil components from the neutralized oil, resulting in clearer and purer crude palm oil (CPO). Continuous clarification tanks or centrifuge are commonly used for this process, where the neutralized oil is heated to a specific temperature to reduce viscosity and improve separation efficiency. The heated oil is allowed to settle or undergo centrifugation to separate oil impurities and water from the oil. Solid impurities settle to the bottom, while water and other lighter impurities rise to the top. The clarified oil, now free from solid impurities and water, is separated from the impurities using decanters or centrifuge. The drying process removes any remaining moisture from the clarified oil to improve its stability and shelf life. Drying may involve heating the oil under vacuum or using specialized drying equipment, where the clarified oil is heated under controlled condition to evaporate any remaining moisture. After drying, the oil is cooled to ambient temperature before further processing or storage. Then crude palm is obtained. After that, the process for the press cake. The pressing process aims to extract crude palm kernel oil (CPKO) from the press cake by applying mechanical pressure. Mechanical pressure such as screw press or hydraulic press are commonly used for this process. The press cake is loaded into the pressing machine. Mechanical pressure is applied to the press cake, squeezing out the oil contained within the kernels. The extracted oil, along with some residual solids, is collected from the pressing machine. The cracking process aims to break break open the palm kernel to facilitate oil extraction. Cracking machines or nut breakers are commonly used for this process. This is where the pressed cake containing palm kernel is fed into the cracking machine. The kernel are subjected to mechanical force to crack open their hard shells, exposing the oil-rich kernel inside. The cracked kernels are separated from the shell fragments using sieve or other separation equipment. The crushing process further breaks down the cracked kernels into smaller particles for efficient oil extraction. Crushing mills or hammer mills are commonly used for this process. The cracked kernel are fed into the crushing machine. The kernels are crushed between rotating rollers or hammers, reducing them to smaller particles. The crushed kernel particles, along with some residual solids, are collected for oil extraction. Then crude palm kernel oil is obtained. The refining process aims to purify and improve the quality of the crude palm oil and crude palm kernel oil. First, neutralization aims to remove free fatty acid (FFA) and other acidic impurities from the crude oil, improving its flavor, color, and stability. In the neutralization of CPO, an alkaline solution is mixed with the oil to react with free fatty acids, forming soap. The soap is then separated from the oil through centrifugation or settling. The neutralization process for CPCO is similar to that of CPO. However, CPKO typically contains higher level of free fatty acid compared to CPO, so a higher concentration of alkaline solution may be required for effective neutralization. Second, bleaching aims to remove pigments, trace metals, and other impurities that affect the appearance and shelf life of the oil. Both CPO and CPKO are mixed with bleaching earth, such as activated clay, and heated under controlled conditions. The bleaching earth adds soap impurities, forming a slurry. The mixture is then filtered to separate the bleaching earth and absorb impurities from the oil, resulting in a clearer and lighter color oil. Third, deodorization aims to remove volatile compounds of flavors and odors from the oil, resulting in a natural flavor and odorless product. Both CPO and CPKO are heated under high temperature and low pressure in a deodorization vessels. This process causes volatile compounds responsible for of flavors and odors to evaporate. The vapor along with the volatile compounds is then condensed and separated from the oil, leaving behind a deodorized oil. Then for CPO, the byproduct will be refined palm oil, which the cooking oil and PFAD stand for palm fatty acid distillate. PFAD is used primarily in the soap and detergent industry as a raw material for the production of laundry soap, toilet soap, and detergent products. It is also utilized in the manufacturing of candles, animal feed, and oleochemicals. While for CPKO, the byproduct are refined kernel oil, which can also be considered as cooking oil, although it is less commonly used for culinary purposes compared to refined palm oil. And PKFAD stand for palm kernel fatty acids distillate. PKFAD has similar application to PFAD. Next, the fractioning process. Initial fractionation, palm olein and palm stearin is produced where the palm olein is the liquid fraction obtained from the fractionation of refined palm oil. It consists primarily of liquid triglyceride with a lower melting point. Palm olein is commonly used as a cooking oil in household and food industries due to its liquid consistency and room temperature. It is also used in food processing, especially in applications where a liquid oil is required, whereas palm stearin is the solid fraction obtained from the fractionation of refined palm oil. It consists mainly of solid triglyceride with a higher melting point. Palm stearin is often used in food manufacturing and bakery applications where solid fats are required, such as in the production of margarine, shortening, and pastry production. Further fractionation of palm olein, we will get one soft olein PMF. Palm meat fraction is obtained through further fractionation of palm oil. It consists of triglyceride with intermediate melting point between palm olein and palm stearin, where the types are mid olein has a moderate melting point and is commonly used in food application such as frying fats, salad oil, and cooking oil. And hard olein has a slightly higher melting points compared to mid olein and is often used in food processing and industrial application. Second, super olein is another fraction obtained from the further fractionation of palm olein. It consists of triglyceride with even higher melting point closer to that of palm stearin, where the type is also mid olein and top olein. The palm stearin, it can undergo splitting to produce oleochemicals, which are chemical compounds derived from natural oil and fats. These oleochemicals are used in various industries, including soap manufacturing, detergent production, and personal care products. Refractioning of palm stearin result in the separation of two fractions, soft stearin, PMF, and super stearin. These fractions contain triglyceride with different melting points suitable for various industrial applications. Soft stearin PMF and super stearin may find application in the production of specialty fats, coating, uh, lubricants, and other industrial products. What is fats? Fats are typically solid or semi-solid at room temperature due to their composition of saturated and or trans fat. The molecular structure of these fats allow them to pack closely together, resulting in a solid state. Fats derived from animal sources and some plant sources contain high level of saturated fats and trans fats. These fats has been associated with an increased risk of heart disease when consumed in excess. Many traditional sources of fats are derived from animal sources such as butter from milk and lard from pork. These fats are commonly used in cooking and baking for their flavor and texture. Due to their molecular structure, fats have a higher melting point compared to oils. This property makes them suitable for use in baking and cooking application where a solid texture is desired. Fats are commonly used in baking to provide structure, moisture, and flavor to baked goods. They are also used in cooking to saute, fry, and roast foods, adding richness and flavor. Additionally, fats are used as flavoring agent in dishes to enhance taste and texture. What is oil? Oil are liquid at temperature due to their composition of unsaturated fats, including monounsaturated and polyunsaturated fats. This molecular structure of these fats prevent them from solidifying at typical room temperature. Oil are rich in unsaturated fats, including monounsaturated and polyunsaturated fats. These fats are considered healthier than saturated fats and trans fats, as they have been shown to lower cholesterol levels and reduce the risk of heart disease. The majority of oils are derived from plant sources such as olive, soybeans, sunflower seeds, and canola seeds. These oils are extracted from plant seed or fruits through pressing or solvent extraction methods. Oil have a lower melting point compared to fats due to their composition of unsaturated fats. This property allows them to remain liquid at room temperature and makes them suitable for use in salad dressings, marinades, or other liquid application. Oil are commonly used in salad dressing as a base ingredient and emulsifier. They are also used for frying and deep frying foods due to their high smoke points and ability to transfer heat evenly. Additionally, oil are used in food processing for baking, frying, and flavoring various food products. The difference of vegetable oil and animal fats based on taste. Vegetable oil typically have a neutral taste, allowing them to adapt to various dishes without overpowering the natural flavors of the ingredients. This natural flavor profile makes vegetable oil suitable for a wide range of culinary application, including baking, sauté, frying, and salad dressings. Compared to animal fats, vegetable oil generally have a lighter taste, which allow the flavors of other ingredients in a dishes to shine through. While most vegetable oils have a mild taste, certain types such as olive oil may have distinct flavor ranging from fruity to peppery, depending on factors like variety and processing methods. Animal fats such as lard and tallow have a characteristic rich and savory flavor profile derived from the animal source. When used in cooking and baking, animal fats add depth and richness to the dishes, enhancing the overall flavor and texture. The flavor of animal fats can vary depending on the source animal, with lard from pork and tallow from beef or mutton offering different taste profiles. Next, based on the stability, vegetable oil contain higher levels of unsaturated fats, which are more susceptible to oxidation when exposed to air, light, and heat. Due to susceptibility to oxidation, vegetable oils have a shorter shelf life compared to animal fats and may become rancid if not stored properly. To maintain freshness, vegetable oils should be stored in a cool, dark place away from heat and light, and sealed tightly to prevent exposure to air. Animal fats, particularly those high in saturated fats, are more stable and less prone to oxidation compared to vegetable oil. Due to their stability, animal fats are suitable for high temperature cooking methods like frying and roasting without the risk of becoming rancid. Animal fats have a longer shelf life compared to vegetable oils, making them ideal for long-term storage and use in traditional cooking practice. Lastly, based on nutrients, vegetable oil are rich in unsaturated fats, which are beneficial for heart health when consumed in moderation. Certain vegetable oils, such as flaxseed oil and hemp seed oil, are high in omega-3 fatty acids, which have anti-inflammatory properties and are essential for overall health. Vegetable oils are low in saturated fats, which may help lower LDL, which is bad cholesterol levels, and reduce the risk of heart disease when used as a part of balanced diet. Animal fats are rich sources of fat-soluble vitamin like vitamin A, vitamin D, and vitamin K2, which play essential role in various bodily functions, including vision, bone health, and blood clotting. Animal fats provide essential fatty acids like arachidonic acid and conjugated linoleic acid (CLA), which are important for brain function, immune health, and inflammation regulation. Animal fats contain high level of saturated fats compared to vegetable oil, which may contribute to increased LDL cholesterol levels if consumed in excess. Oil processing. The process begins with the selection of suitable raw materials, which are typically plant-based sources such as seed, nuts, or fruits. Common oil seed crops include soybean, sunflower seed, rapeseed, and olive. The raw material undergo preparation to facilitate the extraction process. This may involve cleaning, sorting, and conditioning to remove debris, stones, and moisture content, ensuring optimal extraction efficiency. There are two primary methods for extracting oil from oilseed, which are mechanical pressing and solvent extraction. Mechanical pressing: in this method, the oil-bearing seeds are mechanically pressed to extract the oil. The seeds are crushed or ground into a paste, which is then subjected to pressure to release the oil. This process is commonly used for producing cold pressed oils, which retain more of the natural flavor and nutrient of the seeds. Solvent extraction involves the use of food grade solvents, such as hexane, to dissolve the oil from the oil seed material. The solvent is then separated from the oil using heat and vacuum, leaving behind the crude oil. Crude oil contains impurities such as phospholipids that need to be removed to improve the oil quality and stability. Degumming involves the addition of water or acid to the crude oil, which helps in the separation and removal of these impurities. The next step is neutralization, where the free fatty acids present in the crude oil are neutralized using an alkaline solution, typically sodium hydroxide. This process helps in reducing acidity and improving the oil flavor and shelf life. Bleaching is carried out to remove color pigments, residual impurities, and odors from the oil. The crude oil is treated with bleaching or activated carbon, which absorbs the impurities, resulting in a lighter color and odor-free oil. Deodorization is the final step in refining, where volatile compound and undesirable odor are removed from the oil. The crude oil is heated under vacuum to high temperature, causing the volatile compound to remove. This process helps in improving the oil stability, flavors, and aroma. Once the refining process is complete, the refined oil is packaged into containers such as bottles, drums, or bulk containers, depending on the intended market and distribution channel. Fats processing. The process begins with selecting raw materials suitable for the fat production. This includes both plant-based sources and animal-based sources. Raw materials undergo preparation to facilitate fat extraction. This may involve cleaning, sorting, grinding, or rendering. Preparation helps increase the surface area for extraction and remove any impurities or contaminants. Extraction: in the process of separating fats from the fat sources, there are different methods of extracting depending on the source. Rendering, used for extracting fat from animal sources. Rendering involves heating the animal tissue to melt the fat, which is then separated from the solid protein and connective tissue. Mechanical processing or solvent extraction. Similar to oil extraction, mechanical pressing of solvent extraction method can be used for extracting fat from plant-based sources. Once extracted, the crude fat undergoes refining to remove impurities and improve its quality and stability. The refining process is next. Degumming: removing impurities like phospholipids using water or acid. Neutralization or refining with alkali, treating fat with an alkaline solution to neutralize free fatty acids and reduce acidity. Bleaching: removing color pigments, residual impurities, and odor using bleaching earth or activated carbon. Deodorization: removing volatile compounds and undesirable odors through steam distillation under vacuum. Fractionation: separating fats into different components based on their melting point or molecular weight to obtain specific fraction with desired properties. Hydrogenation: it is optional, where it's converting unsaturated fatty acid into saturated or partially saturated fatty acids to alter the physical properties of the fat. Esterification: it is also optional, ranging fatty acid chain to modify the properties of the fats, such as its melting point or texture. Then quality control: implementing measures to ensure that the final product meets quality, safety, and regulatory standards. Refined fat is packaged into containers such as bottles or bulk containers. Packaged fats are distributed to the consumer, retailer, or industry user through various channels.